Since 2004, I'm a professional engineer. Since 2015, various managerial roles. I have various interests, and currently I'm CTO of Scalefocus and director of Scalefocus Academy. So, what is a distributed system? Roughly speaking, you'll find various descriptions online, but most of them include a system built of components that work together in concurrent fashion, and most importantly, they produce more complex behaviors together than they can do on their own. Also, there is a lack of global clock or a global mechanism to oversee and direct every piece of the system. There is an independent failure of components, which basically means that parts of the system or single components can fail, and the system itself can continue to, although at some degraded functionality or performance or whatever, continue to do its job. And most important, and actually the philosophical part, we are not interested in the behavior of the components. In a distributed system, we are interested in the emergent properties, which means properties that are not inherent to any of the components of the system, but only emerge when the components work together. So the best theory, by the way, that we have about what consciousness is emergent property of the neurons working together. So basically, that's a distributed system. Let's see it in action. So basically, to use the words of Douglas Adams, life, universe, and everything else works on distributed systems. Everything that you see is a distributed system. Complex weather patterns, and so on and so forth. So it's natural to use such emergent properties in computing. But why should we go distributed? There is a handful of reasons that are quite strong. First, data. We are in the business of wrangling data, working with data, storing it, computing against it, analyzing it, whatever, distributing it. Data in global terms, every 3 years, pick any 3 years, and get the data that was created by humanity in those 3 years is more than the whole previous history of humanity. Any 3 years consecutive. So basically, that means data is growing exponentially. And we are delivering more frequently, smaller pieces of code and functionality and value. So that's an entirely different topic. We are more frequently delivering compared with the 80s, not compared with 2015. In the last few years, there is a trend actually of having less deployments on average. But compare it with the big picture, we are delivering more and more software ever more often. So, another big reason. Moore's law, to put it for a lack of better word, is dead. Regardless what you can Google online, some people say it is, some people say it's not. In its purest form, it says 18 months, you have twice as many transistors on a chip. That's no longer true. We are in about the 50 to 80 billion transistors per chip now. And there is a physical limit, an actual physical limit, which basically, if the gate length becomes twice as small as now, about 7 nanometers, then quantum tunneling becomes a thing. And we no longer can be sure that we are stopping the flow of electrons past the gate, because they can tunnel on their own due to the Heisenberg uncertainty principle. And don't take it from me, by the way, the founder and CEO of NVIDIA, Jensen Huang, basically said Moore's law is dead 2 weeks ago, actually. You cannot expect the same performance for half the price in 18 months or for the same price, twice the performance. That's not happening anymore, at least not with silicon. There are carbon-based technologies and so on. And on average, you can see the graph per year for the last few years. The average performance gain per year is 3.5%, which is laughable. So we cannot grow higher and produce ever more powerful systems to work with our exponentially growing data. What can we do? So Metcalfe's law basically states that the usability or the usefulness of a system grows with the second power of the number of nodes. So what that means, that's a fancy word, but basically it means when we started hauling bigger loads, we didn't do that by breeding bigger oxen. We just tied more oxen to the load. That's an old practice. We didn't discover that recently. But is there a limit to Metcalfe's law? Can we tie indefinitely many oxen to the load? And it turns out there is. It's called the Amdahl's law. And basically, if you have a part of the process that cannot be stripped down further into smaller pieces and distributed, basically, the longest such process becomes the limit that you can optimize to. Project managers among you call it the critical path of a project. You cannot optimize over that limit. So there is definitely a limit, but Amdahl's law takes for granted that we use the best architecture there is for distribution, and we rarely do. As Conway noted, organizations tend to produce distributed systems that mirror their organizational chart. So flatter organizations produce flatter architectures and more hierarchical organizations, architectures. So we are not even doing the best architectures we can for distribution, so we are far from Amdahl's law. So a few things to beware. So that's Lawrence Peter Deutsch's fallacies of the distributed system. Most developers nowadays creating distributed systems are falling in at least half of those fallacies. I won't go into detail over them. And the other thing is, those are the properties of a distributed system. So it should be resilient, it should be scalable, it should be partition tolerant, it should be effective, and so on and so forth. But the most important part is, everybody knows about them. Some call them architectural significant requirements, architectural quality requirements, and so on. But the thing that most people miss is that all those are connected. For example, if you have to gain more resiliency, you tug and you get less effectiveness because you have to provision more and more. Basically, the system becomes less financially effective, less energy effective, and so on. So those properties are connected, and you cannot get a free lunch. If you get too much of something, definitely you're losing something. If you don't know what you're losing, please make sure to understand that, because down the road, architectures tend to be hard to change. So, other things to beware. By the way, that's called the Brewer's theorem, or the CAP theorem. Eric Brewer is VP of infrastructure at Google. And he coined that theorem for basically distributed storage. So when you have distributed storage, Brewer basically said that, yeah, you can have consistency. Basically, for example, the thing that I read now is the last write to the system, to any of the nodes of the system, for example. That's consistency. Availability, which means whenever I want to read or write, the system is there, and it responds and it behaves in a certain way. And partitioning, or partition tolerance. Basically, the system should be able to be spread out across multiple nodes. Those nodes should be able to fail independently and not bring down the whole system. So, and by the way, there is a cynical description of what a distributed system is. It's a system that failure of a computer that you didn't know existed brings down your own computer. So that basically is poor partitioning. But with a distributed system, we cannot bargain about this. We should be partition tolerant, which means, because the theorem states that from those three, you can get only two. Pick two, any two, but not three. So basically, we are saying, yeah, we are distributed. OK, then do you want to be consistent, or do you want to be available? You cannot be both. That's the gist of the theorem. And some services, like, for example, Airbnb or Booking, choose to be available. Some systems, like banks, choose to be consistent. Many people tend to be angry at banks when their money are missing. So, but that means banks cannot operate 24/7. They do have certain periods in which your transaction will not go through, and so on and so forth, because they need to get their consistency in order. And the other thing is, ACID is quite hard to achieve. So in transactional model, that's atomicity, consistency, isolation, durability. You can usually achieve base, which means basically available. Even though some parts of the system might not be working, you are using at least part of the functionality. Soft state, which means the system itself does not care about making things consistent. Software does. So engineers, if anything is inconsistent, software engineers are to blame. And eventually consistent, which means at some future point in time, the system will be consistent, but you cannot say when. But if you are fine with those, you can have availability. OK. And last but not least, I want to demonstrate how a distributed system works, because it's kind of too abstract, too academic. So imagine, if you will, a coffee shop. A normal coffee shop tries to make money out of the number of cups or the volume they sell. Basically, they have limited time in the day, limited resources. They want to sell as many cups of coffee as they can. So what do they strive for? A coffee shop, you have seen it, no doubt. It has multiple baristas. It has various systems, whatever. It's a distributed system, like the ants making a bridge and carrying over grain. So they can choose. They are distributed, but do they want to be consistent, or do they want to be available? And of course, they want to be available. To give you an example, what a consistent coffee shop would look like is basically to use the so-called two-phase commit. So the first phase, you go to the barista and say, hey, I want whatever, hot chocolate, for example. And the barista would say, yeah, that's fine. And he then locks all the resources he needs, or she, to make that coffee. So milk, hot chocolate, whatever the recipe requires. He will take your card. He will check that your card has the funds necessary, everything. And he will lock those, and no other baristas can use it. That's first phase one of the two-phase commit. And then he will do your coffee, or hot chocolate, or whatever. And they will be sure in that fashion that they will not ever throw any coffee away, because there will be no situations that I start to make coffee, but the milk is out, or the customer doesn't have enough funds to pay for the coffee. They're absolutely sure, but they are able to make less coffee in a day. So they're fine with throwing away some cups, or making the wrong coffee, or making the right coffee, and then discovering that the customer is not able to pay halfway through making the coffee. But they're fine with that, so long as they have throughput. You can always order. That's the important part for them. So that's the basic idea of how a distributed system works. And of course, you know how available coffee shops work. because you have seen those in action. No coffee shop in the world is consistent. So those are a few things to beware when designing distributed systems. If you have any questions, we have 4.5 minutes. Okay. So thanks for the attention, and hopefully it was interesting and you found out something new today. Thank you.